Hello, welcome to this new section of Math 1 M1. We're going to be discussing vectors in this section. There will be 8 videos dedicated to vectors, and the material will be covered over the next 2 weeks. Maybe not the next 2 weeks, depending on when you're watching this, but covered over 2 weeks. In the first video, we're going to just discuss what vectors are, give a basic introduction, and discuss the basic operations we can use when manipulating vectors. So what are vectors? Well, vectors are quantities that have both a magnitude and direction. So we think of them as being like arrows, starting at one point and going to another point. And so the direction is the direction from one of those points to the other, and the magnitude we think of as being like the length or the distance from that one point to the other. So here are 2 possible examples of vectors. U and V, each starting at one point, and then we think of it as an arrow going to another point. So it has a direction, and the length of these lines is the magnitude. We say that 2 vectors are equal if their magnitude and direction are the same. And so, for example, we have here these 2 vectors which are both labeled V. They don't start at the same place, but they have the same direction and length or magnitude, and so we would say that those 2 vectors are equal. There's a bit of terminology here associated with vectors. So they start at one point, and we think then that they go to another point. And so the point that it starts with is called the base, and the point where it ends is the head. So a vector goes from one point, the base, to another, the head. Another thing about vectors is that we can take a negative vector. So if we have one vector u, as shown here, the negative vector, negative u, is going to be a vector that has the same length, same magnitude, but pointing in the opposite direction. So we go from u, you simply turn u around, point it in the opposite direction, and that is negative u. All right, the magnitude, as I've been saying, is the length. We have a notation for the magnitude. Actually, if you look around, people use slightly different notations for the magnitude of vectors. So we may use this same thing that we are accustomed to for the modulus of a real number, or sometimes we use these double lines, like as shown here. And so this is the magnitude or length of the vector u. A unit vector is a vector that has length 1, or magnitude 1. Okay, so a bit more notation. If the point here A is the base of a vector and B is the head, so the vector goes from the base to the head, then we oftentimes will write this notation here, AB with a line over it. Not put myself back in just yet. Okay, so this is all notation, basic ideas of vectors. They have both a direction and a magnitude. Okay, so what are some examples of where vectors might come up? Well, first and most basic example is what is intuitive according to the description I've given, the displacement. So the vector that really points from one point in space to another point in space. And so one possible example is shown here. Maybe some of you aren't in Manchester this year. Usually students are familiar with Manchester, but Fallowfield, area of Manchester, is 3 miles due south of the center of Manchester. So Fallowfield is 3 miles south of the city center in Manchester, and we could have a displacement vector with base at the city center pointing towards Fallowfield. The magnitude would be 3 miles and the direction would be south. Another example of a vector, which is not a displacement vector, so not literally a vector that starts at one point in space and then goes to another point in space, is the velocity. And so the velocity of a moving object is a vector that points in the direction of the motion. That's the direction of the vector. And then the magnitude of the vector is the speed at which the object is moving. Another related vector is the acceleration. So the acceleration is the rate of change of the velocity. So this is also a vector. You accelerate in a given direction. So for example, gravity is an acceleration, or force that causes an acceleration that pulls you always downward towards the center of the Earth. And related to acceleration, I've sort of already said, is the force, which is also a vector. So if you exert a force on an object, that is pushing it in a certain direction, and also the strength of the force, the magnitude of the force, is the magnitude of the vector. And force and acceleration, of course, are very fundamental to how we understand physics, how we understand the world. This is Newton's law, the basic rule for developing mathematical models for the motion of objects, is that the force exerted on an object is equal to its mass times its acceleration. And this is a vector equation. A lot of times maybe you may have seen this as being a scalar equation where you just have force as a single number and acceleration as well. This would be force in a certain direction. But really it's a vector equation. We have 3 dimensions. The force acts in a certain direction and also the acceleration is in a certain direction. Okay, so just another note about the notation here. In these slides, as you can see, I use these boldface letters, U and F, to denote vectors. When I'm working with some examples, as I'll do, I can't really draw boldface, and so I underline the vector. So as shown there, underline U to indicate it's a vector, or sometimes I use an arrow. So I already said the notation from the previous slide. When we have a vector that goes from one point A to another point B, then we put A, B with the arrow over it for that displacement vector. Okay, so these are some notations for vectors. All right, so what about adding vectors together? So the idea of adding vectors together is really quite intuitive. So suppose we have these 2 vectors, u and v. What is u plus v? Well, there's actually a few different ways to do this, or to think about adding u and v. The first one is to think about forming a parallelogram with 2 sides parallel to the vectors u and v, and with the links given by the magnitudes of u and v. So if we have u and v starting at the same point, then this would be the parallelogram shown with the dashed lines. And so u plus v then is the diagonal of this parallelogram. All right, another way, possibly more intuitive, is the triangle law. So rather than putting u and v with the base at the same point, we put the base of v at the head of u. And so arrange them as shown. And then u plus v is this line, or this rather vector, shown there. And you can see that these are equivalent. Here in the parallelogram law, we have just that v is playing the part of this top line of the parallelogram in the triangle law, and in both cases u plus v is this diagonal of the parallelogram. Okay, so if we label things in this diagram now, suppose we have the corners of this triangle, A, B, and C, the 3 vertices of the triangle. Then another way to write this is that we have the vector u, which is the vector from A to B. That's A, B with the line over it. And then the vector v is the vector from B to C. That's B, C with the line over it. And then when we add them together, we get the vector from A to C. And there's a kind of convenient way to remember how this works, of course. You have A to B, you just go from A to B, and then you go from B to C, and so that's equivalent to going from A to C. Forget that you've passed through B along the way. Okay, one thing that's clear from these, particularly the parallelogram law, is that u plus v is equal to v plus u. So if you switch the positions u and v, you get the same result. The addition is commutative. You can do it in either order, just like regular addition. Okay, what about subtraction of vectors? Suppose we have a vector x, which is u minus v. What does this mean? Well, you could think of it as u plus negative v. I already discussed what a negative vector is. It's the same vector with the same magnitude, but pointing in the opposite direction. That is one way to think about it. Another way to think about it is to rearrange this equation. So if you add v to both sides, I use normal algebra we're used to, we have that u is equal to x plus v. And so the picture then, using the triangle rule for the addition of x and v, would be that u is the long side of this triangle, and then x is the vector that points from v to u. So u minus v is the vector from the head of v to the head of u. Okay, so this is addition and subtraction of vectors. There's another operation that we have with vectors, which is called scalar multiplication. And so a scalar is simply a real number here. So r is not a vector, just a regular number. So if u is a vector and r is a scalar, then r times u, written as shown here as ru, is the vector that points in the same direction as u if r is positive, and has a magnitude given by the modulus of r times u. If r is less than 0, then the vector has that same magnitude but points in the opposite direction. All right, so we have this rule for multiplying by -1 as shown. But what if we multiply by some other scalar r? So we have a vector u there. 2 times u would be a vector that points in the same direction as u, as shown here, but has twice the magnitude. -2u would be a vector that points in the opposite direction as u, and has twice the magnitude as well. All right, let's do an example illustrating some of these concepts, the scalar multiplication and addition and subtraction of vectors. So we're going to show that the line segment joining the two midpoints of two sides of any triangle is parallel to the third side and half its length. Okay, let me draw the triangle in question here. I'll label the corners, or the vertices, A, B, and C. And we want to consider the midpoints on two of the sides of the triangle, so let me also label the midpoints on two of the sides, P and Q. So here's P and Q, the midpoints on two sides, and the segment that joins the midpoints is here. And what we want to show is that this segment between P and Q is parallel to the segment between A and C, and half the length. So in terms of vectors, we want to show that PQ, that's the vector from P to Q, the displacement vector, is equal to 1/2 the vector from A to C. AC. So, how are we going to do this? Well, we're going to do it by writing the vector from A to C in several different ways, 2 different ways really. So we'll do this by writing this vector from A to C first as the sum of the vector from A to B plus the vector from B to C. Now this is the triangle rule for the sum of these two vectors. You go from A to B, this vector, plus the vector from B to C, and you get the vector from A to C. Okay, but on the other hand, we can also write the vector from A to C as the vector from A to P, the midpoint, plus the vector from P to Q, plus the vector from Q to C. All right, and so we have this equality here. This is what we'll use. We do need one other thing, which is a relationship between the vector from A to B and the vector from A to P, and the vector from B to C and the vector from Q to C. So how are these related? Well, the vector from A to B is parallel, pointing in the same direction as the vector from A to P, but the vector from A to P is 1/2 the length of the vector from A to B, because this P is the midpoint of the side from A to B. And so we express this as the vector from A to P is 1/2 the vector from A to B. That is, they point in the same direction, and the vector from A to P has 1/2 the length or magnitude of the vector from A to B. And we have a similar relationship between B and C, the vector from B to C, and the vector from Q to C. Right? Q to C is pointing in the same direction as the vector from B to C, and since Q is the midpoint, it has 1/2 the length. And so vector from B to C. Sorry, I've written this backwards. The vector from B to C is 1/2 the vector from B to C is the vector from Q to C. The other way around from the previous one, sorry about that. But still, we have the correct formula. So we plug this in for the vector from A to P, and we plug in 1/2 BC, the vector from B to C for Q to C, and we get vector from A to B plus the vector from B to C is equal to 1/2 the vector from A to B, that's AP, plus the vector from P to Q, plus 1/2 the vector from B to C. Okay, and so now let's just subtract this 1/2 vector from A to B from both sides. And when you subtract it, that one will cancel out. You'll get 1/2 the vector from A to B on the left. And the same thing with this vector, 1/2 the vector from B to C. We're left with 1/2 the vector from B to C on the left. And this equals the vector from B to Q. And now we have 1/2 the vector from A to B plus 1/2 the vector from B to C, which is equal to 1/2 the sum of those vectors. Which is equal to 1/2 the vector from A to C. And so we have 1/2 the vector from A to C is equal to the vector pointing from P to Q, which is what we wanted to show, showing that the vector or the segment from P to Q is parallel to the segment from A to C and has 1/2 the length. Okay, so this is this example giving a feel for the geometric intuition behind vectors and vector addition, scalar multiplication. All right, continue on. So now we're going to talk about how we can represent vectors, specific vectors, and we'll focus for the moment on the plane, so vectors in 2 dimensions. We can also consider, of course, vectors in 3 dimensions. So here we have a vector whose base is at the origin. And there's kind of 2 ways, probably more than 2 really, but 2 ways we'll discuss to represent this vector. One way, labeled A here, is that we give the magnitude of the vector, here the length is 2, but it's just an example, and also the angle made with the positive x-axis. And so these are oftentimes called polar coordinates. You have this angle. In fact, it's really the same as the polar coordinates we talked about when we were talking about integration. We have the angle and the length, and that gives us a vector. Okay, the other way is to specify the x and y coordinates of the head of the vector. So the base, when the base is at the origin, the head will have certain x and y coordinates. So here, if it's 60 degrees, length 2, the x coordinate would be y, and the y coordinate would be square root of 3. All right, and so these are the same vector described in 2 different ways, with the angle and the length, or with the 2 components. For most calculations, the second method, giving the x and y components of the head of the vector when the base is at the origin, is the most convenient. And because of this, we write the vector this way, in terms of the components. So this vector v has components 1 and square root of 3. And we normally will write vectors in this column format here. So the column has the x coordinate on top and then the y coordinate below. An alternate notation we use sometimes is that we write the vector as a combination of what we call basis vectors, I and j. So I is a unit vector pointing in the direction of the positive x-axis, and j is a unit vector pointing in the direction of the positive y-axis. And then this vector is just I plus the square root of 3 times j. This is another notation. All right, we can do a very similar thing in 3 dimensions. Of course, you can use some sort of spherical coordinates in order to describe the direction of a vector and then give the length as well. but that's a bit more complicated and we're not going to cover it here. In 3 dimensions, we'll just talk about using the x, y, and z coordinates to describe a vector. And so here we have a vector whose base is at the origin, and then we describe the vector by giving the x, y, and z coordinates of the head of the vector. So we have this vector, this is saying that it's the vector from the origin, which is labeled as this O, to the point P, which is the head of the vector. And the 3 coordinates in this 3-dimensional coordinate system, well, it might be as shown here. So x coordinate 1, y coordinate 2, and then z coordinate -1. And just to emphasize this, we can also use the notation with the basis vectors, I pointing in the direction of the x-axis, positive x-axis, and then 2 times j, unit vector pointing in the direction of the positive y-axis, and then minus k, k being the unit vector pointing in the direction of the positive z-axis. And so we can write 3-dimensional vectors in either of those notations, either using this column vector or in terms of these 3 basis vectors. Okay, so now let's discuss the magnitude of vector, how we can calculate the magnitude of the vector in terms of the components of the vector. So as I said before, the magnitude of the vector is oftentimes written into using this modulus notation, like the modulus of a real number. And sometimes you see the double bars on each side as well. In 2 dimensions, by the Pythagorean theorem, the magnitude of the vector is equal to the square root of the sum of squares of the components. So square root of a squared plus b squared. And in fact, in 3 dimensions, the formula is exactly the same. You just add the c squared. So square root of a squared plus b squared plus c squared. And this is also by the Pythagorean theorem. So you can work it out. You have to sort of apply the Pythagorean theorem twice in order to get this formula in 3 dimensions. All right, so look at an example. So suppose we have the vector v in 3 dimensions, which is the same one as from the previous slide. The magnitude then is the square root of the sum of squares of the components. So we have 1 squared plus 2 squared plus -1 squared, which is 6. So the magnitude is the square root of 6. And then another thing you sometimes want to do is find a unit vector that points in the same direction as a given vector. So for this particular vector, we write v with a hat over it, as shown here, for the unit vector that points in the same direction as v. So in order to find that unit vector, what we would do is simply divide v by its modulus. And so it's not there on the slide. Let me quickly switch to the visualizer. So we have the vector v with these components, 1 to -1. The modulus of v, as we just discussed, is the square root of 6. The unit vector pointing in the same direction as v is denoted as v with a hat, and I'll still use an underline to indicate it's a vector, but this hat here indicates it's a unit vector pointing in the same direction as v, would be scalar multiplication of 1 over square root of 6 times v. And so the general formula is 1 over the modulus of v times v. It's a unit vector pointing in the same direction as v. Okay. Now, to finish off this lecture, I'm going to go over a few examples. Well, just examples manipulating vectors using the coordinate expressions. And so in this first example, we have 2 vectors u and v, which are given either in terms of the basis vectors for u, or in terms of a column vector for v. And we calculate just u plus v and u minus 2 times v. So let me write u and v again here. As u equals 1, 2, 3. On the slide, it said basis vector I plus 2 times the basis vector j plus 3 times the basis vector k. But this is the equivalent expression using the column vector. V -1, 1, -2. And I won't write that one out in terms of the basis vectors, but you could, of course. And so let's calculate what is u plus v. Now when we add vectors together, we have the geometric definition. We lay the base of one on the head of the other, and then take this third side of the triangle. But we can compute this by simply adding the individual components of the vector. So we have u is 1, 2, 3, plus v, which has components -1, 1, -2. And so when we add these together, you simply add each of the components. So 1 minus 1 is 0. 2 plus 1 is 3. And 3 minus 2 is 1. Okay, so this is the vector you get when you add these two vectors together. All right, let's also compute the other quantity that it mentioned in the example, which was u minus 2 times v. So once again, u is the column vector 1, 2, 3, minus the scalar multiplication of 2 times v, which is -1, 1, -2. And to do this scalar multiplication, we simply multiply -2 by each of the components. So first vector stays the same, and then we multiply each of the components by -2. So -2 times -1 is 2. -2 times 1 is -2. And -2 times -2 is 4. And then we add the components just as before. So this would then be 3, 0, 7. Okay, so it's fairly simple. To do scalar multiplication, you just multiply the scalar by each of the components. And to add vectors, you simply add the components together. All right, another example. Let's consider 2 points, P and Q, and calculate the displacement vector, which points from P to Q. And we'll also find a unit vector in the same direction as this vector from P to Q. So a unit vector that points from P to Q. All right. So just to draw a diagram, and I'm not going to try to draw P and Q in the locations they would be in any coordinate system, but let's just say this was P and this was Q. The vector we're trying to get is the vector from P to Q. And well, the way we want to do this, you can think about this as we have the position vector of P, which is the vector from the origin to P. And we have the position vector of Q, which is the vector from the origin. This is the origin in the coordinate system we're using. The vector from the origin to Q. And so the vector from the origin to P is the position vector of P, which was given as 2, 1, 1. The vector from the origin to Q is the position vector of P, which was given, Q, is given as 1, 5, 4. And this is the vector from the head of P to the head of Q. And if you remember the way when we discussed the subtraction of vectors, the vector from P to Q will be given as the position vector of Q, which is the vector from the origin to Q, minus the position vector of P, vector from the origin of P to P. Okay, so the position vector of Q, or vector from the origin to Q, is 1, 5, 4, minus the position vector of P to 1, 1. And so let's subtract these, and you just subtract the components just like before. So -1, 1 minus 2, and 5 minus 1 is 4, and then 4 minus 1 is 3. So this is the vector from P to Q. Now let's calculate the unit vector that points from P to Q. Right. And the notation now breaks down a little bit because it's quite awkward to then put a hat over this vector from P to Q with the arrow. And so let's actually just call this V. And then the corresponding unit vector is going to be V hat, as in the notation I mentioned before. And so remember, V hat, the unit vector in the same direction as V, is going to be 1 divided by the magnitude of V times V. So I need to calculate the magnitude of V, and this magnitude is 1 divided by the square root of -1 squared plus 4 squared plus 3 squared times V, which was -1 V3. All right, and so let's work out what this is. So 1 divided by 1 plus 16 plus 9 is 26. Square root of 26 times -1, 4, 3. Right, so this is the unit vector pointing from P to Q. So going back up to the diagram, it would be a vector of unit length pointing in this direction. Not trying to draw things to scale here, but it would be vector pointing in the same direction that has length 1. Okay, that's that example. All right, one more example. Now giving a really basic application of vectors. Let's suppose we have two forces, F1 and F2, that are being applied to an object. So remember, forces are vectors. And we want to say what should be a third force so that the object is in equilibrium. So we have an object. There's two forces acting on it. And again, I'm not going to try to draw things in a coordinate system, but I have two forces acting on it. And we want to figure out a third force. Let's call it F3, and so that the object is in equilibrium. And equilibrium means the total force is 0. And so we add up these three vectors. The total force is the sum of the three vectors. And that gives us, well, that will have to be the 0 vector. And so that will give us the condition to determine F3. So what we need is that vector F1 plus vector F2 plus vector F3 equal to the 0 vector. So this is a vector that has all components all 0. So let's say that F3 is equal to A times I plus B times J. So the X component is A and the Y component is B. Then let's write this out. So F1, it was 2 times I plus J. I think this was F1. I know you can't see the slide right now, so you have to trust me that I've copied it correctly, but this is what it said. F2 was I minus 2J. 2. And then plus F3. F3 is A times I plus B times J. And that has to equal the 0 vector. All right, so let's collect all the X or I components, all the coefficient of I. We have 2 plus 1, which is 3 plus A times I. And then let's collect the J components. We have 1 minus 2, which gives -1 plus B times J. And that all has to add up once again to the 0 vector. And so the components of the 0 vector are all 0, of course. And so the two components here have to be 0. So we have to have 3 plus A equals 0 and -1 plus B equals 0, or A equals -3 and B equals 1. So the force that will keep the other two forces in equilibrium, F3, is -3 times I plus J. That's A is -3 and B is 1. Okay, so one more example, this time with an application. So that is the end of the first video on vectors. In the next video, we're going to continue on it and learn how to use vectors to describe the equation of a line, both in 2 and 3 dimensions.